So in this session, we'll be discussing about what do you mean by this electrochemical series, which is also called as activity series. Before going to what do you mean by this electrochemical series, we'll be glancing about two concepts which we have studied in your previous session. That is, one is oxidation potential and reduction potential. Say for example, Mn plus n number of electrons. So what is the reaction happening? It's your oxidation, removal of electrons. So if this is the condition, if metal loses its electron, such type of electrode potential is called as your oxidation potential. Oxidation potential. So if the metal loses electrons, oxidation reaction is happening. So at that electrode, the potential developed is called as your oxidation potential. If this is at standard conditions, if it is at standard conditions, so you know what are the standard conditions? So the concentration is 1 molar and the temperature is 298 Kelvin. It is called as standard oxidation potential. Standard oxidation potential. If the opposite thing happens, that is Mn plus n number of electrons gives you M. So this is your solid, this is your aqueous, opposite this is your aqueous, this is the solid. That is, what is the reaction happening? Electrons has been accepted, so this is a reduction potential. If metal accepts the electrons, then it is called as reduction potential. Reduction potential. And if it is at standard conditions, then it is called as standard reduction potential. Standard reduction potential. Standard reduction potential. So in this standard oxidation potential and standard reduction potential, the PUC has accepted your standard reduction potential as your electrode potential. It is PUC accepted that your standard reduction potential is your electrode potential. That is, wherever you see an electrode potential value, standard electrode potential value, it means that it is the standard reduction potential value of that metal or that element. Then wherever you see if it is standard reduction potential, if it is mentioned standard oxidation potential, say if it is mentioned standard oxidation potential, then what you have to do it? Very simple. So if standard oxidation potential is given, if you want to convert into your standard reduction potential, it is equal to, your standard oxidation potential is equal to minus of standard reduction potential. I think you know this is standard reduction potential, this is standard oxidation potential. Or vice versa, if standard reduction potential is required and if standard oxidation potential is given, you have to do minus of standard oxidation potential. Oxidation potential. Say for example, your Zn2 plus, your zinc's electrode potential is standard electrode potential. Zinc undergoes oxidation, Zn2 plus, it is equal to minus 0.76 volt. So E naught of zinc is minus 0.76 volt. This is your standard reduction potential. This is your standard reduction potential. If I want its oxidation potential, that is standard oxidation potential, what we have to do it is standard oxidation potential is equal to minus of standard reduction potential. So this becomes minus of minus 0.76 volt, that is equal to plus 0.76 volt. So zinc has minus 0.76 volt of standard reduction potential, while its oxidation potential is plus 0.76 volt, which means that the small variation between your oxidation and reduction potential is only your sign change. If one is given with a negative, the value remains the same, the other goes to be your positive. If the standard reduction potential itself is positive, then the other value, standard oxidation potential value, becomes the negative. But remember, IUPAC accepted as your standard reduction potential. Wherever you see the electrode potential for an element, it will be the standard reduction potential. If it is mentioned as standard oxidation potential and you want its reduction potential, do minus of that so that you get your standard reduction potential. So this is about the two things, standard oxidation potential and standard reduction potential. Now let us see what is this electrochemical series is. So this electrochemical series, as you have seen, it is a series, that is it has a series of elements, all the elements with their electrode potential. Remember here electrode potential means it is your standard reduction potentials. So it is a series of elements with their electrode potentials arranged in the decreasing order of their standard reduction potentials. So the element with highest standard electrode potential will be present at the top, and the final bottom will be having the element with standard reduction, least standard electrode potential. So it is a electrochemical series is a arrangement of elements in their decreasing order of standard reduction potentials. Decreasing order. So it's the arrangement of all the elements in their decreasing order of standard reduction potential. That is nothing but your electrode potential. It's nothing but your electrode potential. So highest will be at the top of the series and lowest standard reduction potential element will be at the bottom series. We will not be looking into all the elements that is present in the series. So you can have a look in your NCERT book for the whole table. Here I will be explaining about only some of the very important elements which you should know the values to. So important elements, standard reduction potentials, their values, and what is the oxidizing and reducing nature of those elements we will be looking into the series. Again remembering you, I am not telling all the elements which we have taken in the series. We will be taking only the simple and very important elements which you go through your chapter. So the whole complete series is present in your NCERT. You can go through it and you can correlate these values and the correlations with your NCERT textbook also. So this is your electrochemical series. You can observe that. The first element would be your fluorine. You can observe the reactions here on my left hand side. All are reduction. What do you mean by reduction? It is your addition of electrons. You can observe that the reactions which we have taken is all your addition of electrons, which means that on the right hand side what I have written the values all are standard reduction potential. So all these are your standard reduction potential. As I have already told, standard reduction potential is accepted by IUPAC as your electrode potential. As a result, these are your standard reduction potentials of all the elements. The first element would be your fluorine. You can observe it is undergoing reduction and whose value is highest. It is highest standard reduction value, reduction potential value, it is plus 2.87 volts. Then comes your silver. You can observe these dotted lines means there are a lot of elements in between this fluorine and silver. Since I have already told you I will be taking only the important elements that we will come across in this chapter, the next element will be taken, I have taken is silver. Silver is undergoing also reduction and its electrode potential is plus 0.80 volts. The coming element is your copper. Copper, as we have seen in Daniel cell, I have taken copper also. Copper has undergone reduction to give you the electrode potential. Standard reduction potential is plus 0.34 volts. Then hydrogen. Hydrogen has to be taken because it is present in your sheet. It is taken as the standard hydrogen electrode. That is your reference electrode. Hence hydrogen. Hydrogen is the, I can take it as the mid part of your electrochemical series. So the electrode potential, that is your standard reduction potential of hydrogen, will be 0 volts. As we have taken in She also, the She electrode potential is considered to be 0. Hence hydrogen gas electrode potential is also considered to be 0. Above 0 and below 0, you can divide this electrochemical series into, this is the mid part of your electrochemical series. One will be greater than 0, positive values, the other will be the negative values. Then coming to your iron, iron is also very important since we will be studying about rusting of these iron in your coming sessions. Iron is also important. The reduction potential of iron is minus 0.45 volts. Then coming to your zinc, again zinc is also one of the electrode in your Daniel cell. The reduction potential of zinc is minus 0.76 volt. We have calculated in some problem also. Then coming to your lithium, lithium is the last element its reduction potential is minus 3.05, which means that the reduction potential of this lithium is the least reduction potential. Highest is for your fluorine. The reduction potential cannot exceed over this plus 2.87, neither it can exceed your minus 3.05. So these are the two extremes of your standard reduction potentials. Now let us see what is the consequence of these positive values, that is what do you mean by these positive values and what do you mean by these negative values. So the standard reduction potential value, if it is positive, which means that its standard reduction potential is very high, which means that the reduction reactions happen very easily, or this fluorine is ready to reduce itself very easily. So the positive values means its reduction potential is very high and it readily undergoes reduction. So if E0 value is greater than 0, that is positive values, it means the species undergo, or elements undergo easy reduction. For example, fluorine has highest standard reduction potential of plus 2.87 volt, which means that fluorine is ready to undergo reduction. That is, it accepts the electron from other species, itself undergoes reduction. What do you call such species as, which grabs the electron from other species and itself undergoes reduction, is nothing but your oxidizing agent. So itself undergoes easy reduction means it is an oxidizing agent. So these elements whose value is greater than 0, that is positive values, species undergo easy reduction, which means these are oxidizing agents. That is, it oxidizes other species. Fluorine oxidizes other species, itself undergoes reduction. Hence, it is a very good oxidizing agent. So this is a very good oxidizing agent. If you go from fluorine to copper, you can observe the values is decreasing. That is, the positive values is going from 2.87 to 0.34 volts, which means that the oxidizing property, that is oxidizing power, decreases from your fluorine to copper. Then it becomes 0 here. So lower the positive values, which means that the oxidizing power decreases from fluorine to copper. However, here hydrogen is 0. That is, it can act as both an oxidizing agent and a reducing agent. That is, it can act as a cathode as well as an anode. We have studied in your sheet. Now, if you observe below 0, the values are going to be negative. That is, E0 values, if it is less than 0, that is negative values, it means that the species do not undergo easy reduction. That is, the elements below these hydrogen, that is your iron, zinc, lithium, instead of undergoing reduction, they give electrons. Instead of accepting electrons, they are ready to give electrons. What do you call these as, which gives readily electrons? That is nothing but your oxidation happens very easily than your reduction, which means that these elements below your hydrogen, instead of undergoing reduction, they undergo oxidation by giving some electrons. So these species which give electrons are called as your reducing agent. It reduces other species, itself undergoes oxidation. So hence, these elements below your hydrogen, they readily give electrons instead of accepting electrons. Hence, they are called as your reducing agents. So these are your reducing agents. Reducing agents. That is, The elements above the hydrogen are good oxidizing agents. They accept electrons from the other thing, itself undergoes reduction and other species undergo oxidize. So as a result, oxidizing agent. While if you come to the lithium, it is the best reducing agent, that is it readily gives electrons when compared to your all these above elements. As a result, lithium I can call it as the best reducing agent. Reducing agent. This is the best oxidizing agent. Best oxidizing agent, and this is your best reducing agent. So by looking at your standard reduction potential, you can decide whether a species, whether an element can act as an oxidizing agent or a reducing agent. If the values are positive, if the E0 values are positive for an element, it is a very good oxidizing agent, that is it oxidizes other species, itself undergoes reduction. If the values are negative, it easily undergoes reduction, that is it reduces other species, itself undergoes oxidation very easily. So if you look into the oxidizing power and reducing power trend from fluorine to lithium. Fluorine is the best oxidizing agent because its standard reduction potential is positive, which goes on decreases, reaches 0, then goes to negative, which means that from fluorine to lithium, the oxidizing power goes on decreases. So oxidizing power decreases, or I can also call it as oxidizing nature of the element decreases. That is the oxidizing agent acting as an oxidizing agent, its capacity decreases from fluorine to lithium. If you look into the reducing agents are those whose SRP, standard reduction potential, should be highly negative. So this is your best reducing agent, which means that its value is highly negative. If you go on moving to the fluorine, it becomes positive, which means that reducing power decreases from lithium to fluorine, or I can call it as reducing power increases from fluorine to lithium. Oxidizing power decreases while your reducing power increases from fluorine to lithium. So reducing power, reducing nature increases from your fluorine to lithium. So reducing power increases, oxidizing power decreases. Fluorine is the best oxidizing agent, while lithium is your best reducing agent. So if you give any three elements, say for example X, Y, Z, say for example X, Y, Z, if its E0 values are given, say E0 value here it is, say 0.1 plus 0.1 volt, say this is minus 0.1 volt, say this is minus 2.4 volt, you can know which is the best oxidizing agent and which is the best reducing agent. Best oxidizing agent is the one whose standard reduction potential should be highly positive. The best reducing agent is the one whose E0 value should be highly negative. So if you look into these three values, one is positive, two are negative. The best oxidizing agent is one with positive value. So this X will be your best oxidizing agent. The best reducing agent will be your Z because its value is highly negative. So like this you can have an order, you can arrange it while looking into the values of E0 by knowing whether it is positive or negative and what is the extent of those negative values. You can decide which is the best oxidizing agent and best reducing agent. So here it is, if I want your oxidizing power, so it goes like X is highly oxidizing than Y, which is highly oxidizing than Z. So this is your oxidizing nature. Oxidizing nature. That is because X has a positive value, which means it is highly oxidizing agent. Y is having negative, even Z is having negative, but the extent if you look into, it is just 0.1 volt. This is minus 2.4 volts, which means that Z is least oxidizing when compared to your Y. So like this, you can have a arrangement of elements, or you can also know which is acting as an oxidizing agent and a reducing agent by this electrochemical series. The next topic we are going to discuss in this session is very important, and you have numericals based on this. That is your Nernst equation. Nernst equation, we'll be directly going into what is this Nernst equation. So let us see reduction reaction, oxidation reaction like this. Metal give rise to Mn plus N number of electrons. The Nernst equation for this reaction, remember this is a half reaction, half cell reaction, only one metal I have taken, and this half reaction is your oxidation half reaction. Remember this is a oxidation half reaction. For this I will be writing your Nernst equation. So Nernst equation is a relationship between the cell potential and standard cell potential. That is, this Nernst equation gives a relationship between E and E naught. E and E naught. What is E? E is your cell potential. What is E naught? E naught is your standard cell potential. What is the difference? Very simple. This E is the cell potential at any instant, any concentration, any temperature. E naught is the cell potential at standard conditions, that is at 1 molar concentration or 1 atmospheric pressure as well as 298 Kelvin temperature. So that's the difference, and the relationship between these two things, E and E naught, is nothing but your Nernst equation. So for this oxidation half reaction, we will be taking your Nernst equation. So Nernst equation will be E is equal to E naught minus 2.303 RT by NF log of product divided by reactant, that is Mn plus divided by M. Product is your Mn plus divided by M. So what are these R value? R is your gas constant, it is 8.314 joule per mole per Kelvin. Then T is your temperature, 293 Kelvin, that is your 25 degrees Celsius. T is 293 Kelvin. N is your number of electrons accepted or liberated, or number of electrons change in the reaction. Then F is equal to 1 Faraday, that is the charge of 1 mole of electrons, that is equal to 96,500 coulombs. So these all are your constants, R, T and F are your constants. If I replace these R, T value as well as Faraday's value in this equation, the equation would be modified into E is equal to E naught minus 0.0591 divided by N. N depends upon each cell. As a result, you cannot have a constant on this. N depends on each cell. So N log of product Mn plus divided by M. That's your reactant. So if you observe this is a reduction half cell. For this reduction half cell, it is the Nernst equation becomes E is equal to E naught minus 2.303 RT by NF log of product divided by reactant, that is M divided by Mn plus. Again, if I substitute these values, R is your gas constant, T is your temperature, 293 Kelvin, N number of electrons, F is 1 Faraday, 96,500 coulombs. If I substitute it, it becomes E is equal to E naught minus 0.0591 by N log of product divided by reactant. So this becomes for your reduction half reaction. Now let us see what happens for your complete cell, that is if you have a both reduction half reaction and oxidation half reaction. What about this Nernst equation? Let us see for that. So Nernst equation for a cell, the cell I am going to take is your Daniell cell, for your Daniell cell. So what is the cell reaction? If you look into the cell reaction, zinc undergoes oxidation, copper undergoes reduction. So Zn solid plus Cu 2 plus aqueous give rise to Zn 2 plus aqueous plus Cu solid. This is your reaction for Daniell cell, the complete reaction, that is zinc has undergone oxidation, copper has undergone reduction. So this is your complete reaction for cell reaction for your Daniell cell. So by looking into this, if I have to write your Nernst equation, what will be your Nernst equation? Nernst equation is E is equal to E naught cell. This is your not your half reaction. As a result, I have written E cell. E cell is the cell potential. This is your standard cell potential. E naught cell minus 2.303 RT divided by NF log of product divided by reactant. So product is Zn2 plus and copper. Remember, for any pure element in standard states, that is in your solid, liquid or a gas, the concentration of those pure states of metals will be equal to 1. That is, the concentration of copper here will be equal to 1. So any element in its standard free state, its concentration is to be taken as 1. So as a result, if I take here Zn2 plus into copper becomes equal to 1. As a result, here it is concentration of Zn2 plus into copper, but we know that copper is equal to 1. So as a result, I will not consider this copper here because its concentration is 1. Divided by reactant divided by product. Product divided by reactants. What are the reactants? Zinc and copper 2 plus. Again, it is in its elemental state, its concentration is 1. So this is equal to concentration of Cu2 plus into concentration of Zn. But as I have told you, the elemental state concentration is equal to 1. Hence, I can also delete this one. Think that in this balanced chemical equation, you can observe the coefficient of each element is equal to 1. Think that you have a cell reaction wherein you have a different quotient, that is different coefficient for this. Say this is 2. If this is 2, say here this is 2. What you have to do is you have to raise to the power of its coefficient. What is the coefficient? Chemically balanced equations coefficient. You have to raise into it. That is, here I can write it as raised to the power of 1, raised to the power of 1, which means it is one and the same. The concentration of Zn2 plus divided by concentration of copper 2 plus. This is because you have studied in your equilibrium a law which means that the molar concentration of your products divided by reactants raised to the power of their stoichiometric coefficients, which means that in the chemically balanced equation, if you have other than 1 as your coefficient, you have to raise these concentration to that coefficient. Since here it is 1, the coefficient all over the equation, the coefficient, stoichiometric coefficient is 1, I have raised here it to 1, which means one and the same, the concentration of zinc. If it is 2, 3 or the other, you have to raise it to this respective coefficient, stoichiometric coefficient. So this is for your Nernst equation for your Daniell cell. If I substitute your R, T and F value, the equation becomes E cell is equal to E naught cell minus 0.0591 divided by N log of concentration of Zn2 plus divided by concentration of Cu2 plus raised to the power of 1. Raised to the power of 1. Remember, in Daniell cell, N is equal to 2. What is N? Number of electron transfer. You can observe Zn to Zn2 plus 2 electrons, copper 2 plus to copper, which means that 2 electrons. So here N is equal to, remember here N for Daniell cell is equal to 2. It goes on changing for different cells. If you have a magnesium and iron or silver and iron, it goes on changing. That will be obtained by having this chemically balanced equation, which you will be seeing in your numericals. But remember, in your Daniell cell, N is equal to 2. Number of electron transfer is 2. So this is your Nernst equation for your Daniell cell. What about a general equation, Nernst equation, which is holding good for any cell? What is that? Very simple. You can write it as a general equation, a general Nernst equation, which holds good for any cell. That is, E cell is equal to E naught cell minus 0.0591 divided by N. N depends on what is the type of cell, what are the electrodes used, log of zinc. What is zinc happening? Oxidizing, it is happening oxidation. As a result, It is log of oxidized species, concentration of oxidized species divided by reduce. So what is happening for copper? Copper is your reducing species. It undergoes reduction. As a result, it is by reduced species. So this will be your Nernst equation that holds good for any cell. So if you take any cell, if you want to apply Nernst equation, it will be E cell is equal to E naught cell minus 0.0591 by N. N is number of electron transfer, log of oxidized species divided by log of concentration of oxidized species divided by concentration of reduced species. Remember, raised to the power of their stoichiometric equations, the stoichiometric coefficients that is present in a chemically balanced equation. If it is equal to 1, no need to write it, but if it is more than 1, you have to write the stoichiometric coefficients of both the oxidized species as well as your reduced species. So E is your reduction potential of the cell, E naught standard reduction potential of the cell, N number of electron transfer, oxidized species divided by reduced species raised to the power of their stoichiometric coefficients. By applying these equations, you have to do some numericals which will be discussed in your next session.